I'd like to include one more proof that I present here as part of the lecture, and it's partly for practice with these kinds of ideas, partly for fun, and partly I just like the result, and I want to go through some interesting results. So this one is about cancelability. So here's what I mean by that. And by the way, this is part 2 of Theorem 79. So I think what I'll do is make part 1 a possible presentation problem if you want to. Part 1 is about injections, part 2 is about surjections. And they're both cancelability results. So here's part 2. So suppose you have a function h from z to x. So I'm going to maybe write it like this. H goes from z to x. And assume h is surjective. So now I'm imagining that every element of this set is h of something. That's surjective, right? Every element of this set is h of something from this set. Okay, I'm assuming those things. Now assume you have f and g mapping x to y. So here's y, and I have f being a way to go from x to y, and I also have g being a way to go from x to y. Now, in this context, since h is z to x and f is x to y, h is z to x and g is x to y, the compositions f composed with h, g composed with h, are nice ones, right? I'm guaranteed that f composed with h, g composed with h, go from z, from the beginning to the end, to y, right? Both are going to be z to y. That's something I know due to the essence of composition, this thing that I keep using here. Now, I'm going to assume that if you go h then f, so f composed with h, then you get something that's the same as if you go h then g. So f compose h equals g compose h. Then the claim is that in this context, you can cancel the h's. So there's an h on the right side on both sides. I claim that you can cancel the h's. So the claim is f equals g. So this is pretty cool. It's a cancelability result in a context where, the thing you're canceling might not actually be an invertible function. But just because it's surjective, it's going to end up being cancelable. Some fun things you might want to think about if you want to. If h is not surjective, then can you find an example of a non-surjective h where the cancelability fails? Another thing that might be fun to think about. So by fails, by the way, I mean you have f compose h equals g compose h, but you do not have f equals g. Another fun thing to think about is, what about the other direction? So what about this? If all you knew was this, and if h was, say, instead of z to x, h is y to z, so that these compositions are the right kind of thing, then would you be able to cancel the h's? I think it should not be something you can do. So it's fun to come up with counterexamples for those kinds of things. All right, but let's prove what does work. If you have a surjection, then it can be canceled when it's showing up on the right on both sides. Okay, so before I erase that picture, let me just go ahead and say right at the beginning of my proof that I know f compose g, g compose h maps z to y thanks to Theorem 63.2. So let's just get that out of the way. I don't know how it's going to help right away, but I know I'm probably going to need it. So by Theorem 63.2, f composed with g and h composed with g composed with h, sorry, f composed with h and g composed with h, both map z to y. Okay, let's get this stuff out of the way. I think I want to keep staring at this diagram while I work on this. So let me get this out of the way. then how about I just shrink this? Keep it kind of in the corner. All right, so that actually crashed my program. Apparently, if you try to, so my program periodically autosaves what the board looks like. Apparently, if it autosaves while I'm resizing an object, that causes a crash. Pretty interesting. Okay, so I rewrote everything, and here's my diagram. H goes Z to X, capital X, and then F and G are different ways of going X to Y. Okay, and the claim is from F compose H equals G compose H, the claim is F equals G. Proof. Okay, I also forgot that I had this already up. By theorem 63.2, these compositions both map Z to Y. Okay, so these are two ways of going from Z to Y. So then, these two are functions, right? So F composed with G, G composed with H, are then functions with the same domain. Namely, Z. Z is the common domain. So I'm in this perfect setting for applying theorem 53 for equality of functions. I have two functions, they have the same domain. Now if I want to prove they're equal, then it's sufficient to prove that they have the same output for any given input. So now I'm going to try to prove this kind of thing. But instead of the functions being f and g, the functions are called... Oh wait, they are f and g, never mind. Yeah, I'm trying to prove literally this thing with f and g. So consider any x in the domain of f. So consider any x in that common domain. It's called z, so let me just call it z. Actually, if I'm going to go along with the theme of using lowercase letters to go with capital letters, how about I call it little z instead of little? Wait a second. Wait just a second. Okay, I'm actually trying to prove f equals g. So I care about f and g being functions and the domain of f equaling the domain of g. I don't care about these two, which I even misspelled. Wow, okay. Let's be a little bit more careful. So f and g are functions. And the domain of f equals the domain of g, namely it is x. Okay, my goal is to prove f equals g. Now I'm in a situation where I can apply theorem 53 to prove that f equals g by proving that they have the same output for any given input. So consider any little x in the domain, which is this big X. So how in the world am I going to prove that f of little x equals g of little x? That's what I have to do right now, right? So goal here is prove this. How in the world are we going to do that? Well, somehow we have to use this fact, right? Otherwise it would be impossible. Why would two random functions just be equal? So somehow we have to be focusing on this. How do we use this? What can we do to use this? Well, one way to think about this is actually to think about it along the lines of theorem 53. Sort of. Just plugging in inputs and then saying, well, the outputs match up. I say sort of because it's a really trivial part of theorem 53. It's actually more like, axiom 2, theorem 4, just this idea that when two things are equal, then they just behave the same way. When two things are equal, if you take any expression and replace one thing by something that it's equal to, then you get an equal expression, term. You get an equal term. So this is just true for any x. Okay, x is a terrible letter to use there, because I'm not talking about that kind of x. But this is just true for any, what should I call it? How about little z? trying to make it extra curly to distinguish it from the capital Z here. This is the capital Z. Yeah, so this is just true, right? And this is for any little z. And actually, this is like f of h of little z, right? That's how a composition works. This is g of h of little z. So this is what I actually know. I know that f of h of anything equals g of h of that thing. So as long as the thing that I'm putting inside of f and g takes the form h of something, then I know that f and g agree on that kind of input. I'm trying to show that f and g agree on x here. So are you seeing a strategy sort of coalesce? If we can show that x has the form h of something, then we can use what we know, namely that f and g agree whenever you input h of something. So does x necessarily have the form h of something? Yes, h is surjective, right? It's surjective onto x. So the little x that I started with over here comes from somewhere. It comes from some little z over here. And now we have a strategy. Since h is surjective, we can get, this is existential instantiation, there is some little z back here. We can get little z in big Z such that h of little z is x. Then f of x. Okay, let's see if we can get from f of x to g of x. So f of x is f of h of little z, right? Because x is h of little z. And that is equal to f composed with h of little z. That's by essence of composition. So this is just like theorem 4, right, from here to here. And then from here to here, that's this is 63.1. So this is like theorem 4. This is theorem 63.1. And then this is one of our hypotheses, one of our assumptions, right? Assume that f composed with h equals g composed with h. Along with theorem 4 also, I guess. And that's g of h of z. So again, we're using essence of composition. And that's g of x. So again, using theorem 4, just replace h of z by something it's equal to. There you go, f of x equals g of x. By theorem 53, the equality of functions theorem, since we have pointed out the domains are equal and that the outputs match up, f of x equals g of x for any given x, f equals g. So we're done here. The cool thing about this, proving this kind of theorem, I think, is the whole thing kind of plays out on this diagram. The diagram is this stage on which the entire proof is playing. So, you look at this diagram and you think about the assumption that if you go h then f or h then g, then those should be equal ways of going from z to y. So that's our assumption. That if you go take this path or you take this path, and when applying functions to any particular element, then those are equal. Those are the same. So start with that assumption, then try to prove from h's surjectivity that f equals g. So start with something here. That's what we called little x. Since h is surjective, that comes from something back there. So there's some little z that h maps over to little x. H of z is x. Then our goal is to prove that f of x and g of x are the same. Since we were able to get this z, we know that if we do hf, or fh, depending on the order in which you write your compositions, if you do h to z and then f to that, that should be the same as if you do h to z and then g to that. So this and this are the same. Therefore, from x, you end up in the same place whether you go this way or this way. It's just neat how the entire thing is playing out on this diagram. And you're sort of chasing elements around the diagram. This happens a lot in mathematics. These kinds of arguments, they're called diagram chases. And these are actually called diagrams, these kinds of pictures where you put sets and arrows and names of mappings between different sets. So this is a diagram chase, and this happens all the time. Okay, so that was 79.2. 79.1 is a presentation problem if you want to choose that one. I think it's probably not as easy as the other presentation problem, but it would probably be more interesting. And from here in the course, we're actually going to sort of stop here. So Theorem 79 is our last official theorem of this section. So this is our section on composition. Right, here's our table of contents. So we're on the section 3.7. We're actually going to skip section 3.8 so that we can fit in as much as possible of this natural numbers, induction, recursion, addition, as much as possible of this stuff into the end of the quarter. Okay, so our plan is skip section 3.8, and then we're going to stop with section 3.7. We're going to stop right here. So Theorem 79 is our last official one. A particular highlight among some of the things that we're skipping here is this axiom. This is the first time you see an axiom for a while, actually. We're never going to use this axiom in the later stuff, except in some exercises that I'm not going to assign. But if you're interested in learning about the axiom of choice, you might take some time, or maybe take some time after the quarter is over, and look at the rest of this section. I mean, the rest of section 3.7. So this axiom, some people will include it, some people will not include it, depending on what they're trying to do. But for modern math, you pretty much need it. And you can see it's kind of, it's about composition and inverses and these kinds of things. That's why it fits in here. So it's about when you can take a function, a surjective function, when you can take a function and get a right inverse for that function. So we've seen sort of that when you have an injection, like f is an injection, then there's a left inverse, namely f inverse would be the left inverse. So you compose this thing on the left and you get identity. What about composing on the right to get an identity? If you have a surjection, can you always do that? Then the axiom of choice is all about that. Is the answer yes, you can. It has to be done by axiom. Okay, so that's like optional reading, and I think it's totally acceptable to look at this after the quarter is over if you're interested. So that means next time we will pick up from here, definition 89, and we'll finally define the numbers.